Keeper 4.7, implicit differentiation. All right, so we use implicit differentiation when we want to take the derivative of an equation that has x and y on both sides. So instead of having to solve for y first, we can just do implicit differentiation to get our answer a lot quicker. First example, we want to find the first and second derivative of xy plus y squared equals 1. All right, so let's start with the first derivative. The derivative of xy, remember we have to do product rule, so I'm going to do first times the derivative of the second, but remember the derivative of y is dy dx, plus second times the derivative of x, which is 1. And then we're going to move on to the derivative of y squared, which is 2y, but again, I have to put that dy dx because I took the derivative of y. And that all equals 0 because the derivative of 1 is 0. From here, I'm going to move everything that doesn't have a dy dx to the other side of the equation, and I'm going to group everything with the dy dx, and I'm going to leave that on the left side of the equation. So once I've done that, I can divide out by the expression in front of the dy dx, so I can divide out by x plus 2y to get dy dx by itself. Therefore, my first derivative is negative y over x plus 2y. Now let's look at finding the second derivative of this problem. So again, the first derivative is negative y over x plus 2y. And to find the second derivative, notated as d squared y over dx squared, I'm simply going to use quotient rule. So I'm going to do low, which is x plus 2y, d high, which is 1 or negative 1 dy dx, minus high, and then d low, which would be 1 plus 2 dy dx, over low, which would be x plus 2y squared. From there, everywhere I see the dy dx, I want to substitute in what our actual dy dx is. So I want to substitute in that first derivative. And you can see it written here in blue. After that, I'm pretty much done. I just need to simplify my expression to make it look a little bit better. So I'm going to start condensing everything, add my like terms, and when I finish, I'm going to end up with 2y minus y squared, 2y squared over x plus y, all over x plus y, 2y squared. All right, again, we don't really like having the double fractions, so the easiest way to get rid of this is to multiply everything in the expression by x plus 2y. In doing so, I get a nice pretty expression with one fraction bar of 2y times x plus 2y minus 2y squared over x plus 2y cubed. And finally, just simplifying a little bit more, I get 2xy plus 2y squared over the x plus 2y cubed. All right, in our next example, we have 2xy plus pi sine y equals 2 pi. And again, I want to find the derivative. This time I'm only finding the first derivative, but I want to find it at the point 1 pi over 2. So again, to start this, I'm going to start with the product rule, and I have first times the derivative of the second, plus second times the derivative of the first. And then the derivative of pi sine y would be pi cosine y equals 0 again. Now, it's 0 because the derivative of 2 pi is 0. Notice that every time I took the derivative of y, I put the dy dx, because we know that if we're taking it with respect to x, we have to include that when we take the derivative of y. Again, I'm going to try to isolate the dy dx, so everything that doesn't have dy dx is going to be moved to the right-hand side of the equation, and then everything that does have the dy dx, I'm going to leave on the left side, but I'm going to factor out that dy dx. Finally, dividing out by the 2x minus pi cosine y, I get dy dx equals negative 2y over 2x minus pi cosine y. Now, they asked us to evaluate it at 1 pi over 2. So I'm using my notation. This straight up and down line means such that. So I have dy dx such that xy equals 1 pi over 2. And then I'm just going to plug in that 1 pi over 2 for my x and my y. Once I get that, I can simplify, and I'm left with negative pi over 2.